So, good day, Ma'am Silenio. Here I am to report the chemistry of water treatment. So, the first part is introduction about drinking water standards. I will be talking about primary drinking water standards, secondary drinking water standards, and other rules promulgated by EPA. But first, standards for drinking water vary according to the type and size of water system. And first example of it was a community water system. It is the one that serves the same people year round. Example include those in cities and small towns that provide water to residences, home, condominiums, and mobile home parks. Next, a non-community water system. It is the one who serves the public but does not serve the same people on a year-round basis. A non-transient non-community water system. It is defined as one which serves the same people for 6 months but not year-round. Sample school. Rest areas and campground are considered transient non-community because they serve the public but do not serve the same individuals for more than 6 months. Next is rest areas and campgrounds are considered transient non-community because they serve the public but do not serve the same individuals for more than 6 months. So, drinking water standards for various contaminants have been established by the U.S. Environmental Protection Agency as authorized by the Safe Drinking Water Act. And drinking water standards are classified either as primary or secondary. First, what is primary drinking water standards? It is the one that are established to ensure safe, finished water. It includes microbiological organisms, disinfection by products, organic chemicals, and many of which are priority pollutants, inorganic chemicals, radionuclides, and turbidity. While secondary drinking water standards are not related to health and are therefore non-enforceable by the US EPA. They also relate to the aesthetics of the water, making it more desirable to the consumer. For other rules promulgated by EPA, it includes Groundwater Rule, Long-Term 2 Enhanced Surface Water Treatment Rule, Stage 2 Disinfectant and Disinfection by Products Rule, Long-Term 1 Enhanced Surface Water Treatment Rule, Filter Backwash Recycling Rule, Arsenic Rule, Stage 1 Disinfectants and Disinfection by Products Rule, Interim Enhanced Surface Water Treatment Rule, Lead and Copper Rule, Total Coliform Rule, Surface Water Treatment Rule. So, for the overview of typical used for contaminant removal. The following discussion presents some of the typical processes used for removing various contaminants from water, and some of the parameters that may be adjusted by chemical addition. Number 1 is alkalinity. The alkalinity of the water may be insufficient to resist a change in pH when certain coagulants or coagulant acids are added to the water. Generally, lime, caustic, or soda ash is added to the water to increase the alkalinity. Arsenic. Arsenic dissolved in water is found as arsenite or arsenate. Coagulants such as alum, ferric chloride, ferric sulfate, and lime have been successfully used to remove arsenic from water. However, arsenic must be in the form of As5 for a coagulation to be effective. If in the form of arsenite, As3 first, it must be oxidized to As5 by adding chlorine or permanganate. Next is barium. Barium can be removed effectively by lime softening. Greater than 90% removals have been achieved in the pH range of 10 to 11 on groundwater containing 7 to 8.5 mg per liters of barium. Kawamura indicates that barium can be removed by either lime softening or by ion exchange with a sodium regenerate cycle. For cadmium, coagulation have also been used for cadmium removal, but their use is not as effective as lime softening. Next is chromium. Chromium can be removed easily by using alum or iron salts and by lime softening. Aluminum and iron salts or lime softening are not effective at removing chromium-6. Ferrous sulfate first must be used to reduce chromium-6 to chromium-3 for these coagulants to be effective. Next is color. Color removal traditionally has been accomplished by oxidation with chlorine, chlorine dioxide, oxygen, or potassium permanganate. Granular activated carbon and powder activated carbon can also be used for color removal. Fluoride. Fluoride can be removed during lime softening if the magnesium concentration is high according to AWA. Next is gases. Dissolved gases that may be found in groundwater include hydrogen sulfide, carbon dioxide, methane, and volatile organic chemicals. Carbon dioxide is typically removed by air stripping, and stripping of these gases is normally accomplished by tray aeration, puck tower aeration, cascade aeration, fountains, and spray aeration nozzles. Diffuse aeration is sometimes used instead of air stripping. 9 is iron. Dissolved iron must be oxidized to Fe3 before it can be precipitated and removed by sedimentation and filtration. Lead. Lead can be removed by coagulation and lime softening. Kawamura also indicates that lead can be removed by ferrous sulfate addition at a pH of 7 to 9, alum coagulation at a pH of 6 to 9, and lime softening at a pH of 9.5 to 11.3. Next is manganese. Manganese 2 is the dissolved form like iron must be ionized or it must be oxidized to Mn4 in order to precipitated and removed from water. Mercury. Kawamura stated that inorganic mercury can be removed by coagulation with ferric sulfate at a pH of 7 to 8 and by lime softening at a pH more than 11. Granular and powdered activated carbons are effective at removing organic mercury from water. Nitrate is relatively unaffected by conventional treatment consisting of coagulation, flocculation, sedimentation. Ion exchange is the simplest and lowest cost method of removing nitrate from contaminated groundwater. Often, for the next is pH. Often, the pH of the water must be adjusted by adding either an acid or base. Sulfuric acid and phosphoric acid can be added to lower the pH, whereas lime or caustic soda is added to raise the pH. Radionuclides. The best or the principal source of natural radionuclides is uranium ore. In full-scale experiments, lime softening removes 70 to 95% of influent radium concentration. The best available treatment for radium-222 is aeration, while combined radium and radium-228 treatments consist of coagulation and flocculation. 16 is taste and color. Taste and color compounds may be related to organic compounds, secretions from algae, and or inorganic compounds. Activated carbon is the most effective means of removing these compounds, whereas chlorine oxidation is the least expensive method. Next is total organic carbon. Total organic carbon can be removed by lime softening and or coagulation. However, coagulation is more effective than just using lime softening. So for this topic, we will be discussing about coagulation. So what is coagulation? The object of coagulation is to turn the small particles of color, turbidity, and bacteria into larger flocks. These flocks are then conditioned so that they will be readily removed in subsequent processes. Technically, coagulation applies to the removal of colloidal particles. However, the term has been applied more loosely to removal of dissolved ions, which is actually precipitation. Colloid stability. The particles in the colloid range is are too small to settle in a reasonable time period, and too small to be trapped in the pores of a filter. For colloids to remain stable, they must remain small. Colloid destabilization. Colloids are stable because of their surface charge. In order to destabilize the particles, we must neutralize this charge. Such neutralization can take place by the addition of an ion of opposite charge to the colloid. Since most colloids found in water are negatively charged, the addition of sodium ions should reduce the charge. So what is its purpose? The purpose of coagulation is to alter the colloids so that they can adhere to each other. During coagulation, a positive ion is added to the water to reduce the surface charge to the point where the colloids are not repelled from each other. A coagulant is the substance that is added to the water to accomplish coagulation. And there are three key properties of coagulant. First, the trivalent cation. As indicated in the last section, the colloids most commonly found in natural waters are negatively charged. Hence, a cation is required to neutralize the charge. A trivalent cation is the most efficient cation. Next is the non-toxic property. This requirement is obvious for the production of a safe water. And the third is insoluble in the neutral pH range. The coagulant that is added must precipitate out of solution, so that high concentrations of the ion are not left in the water. Such precipitation greatly assists the colloidal removal process. So there is a table here that that shows list of coagulants and chemical use during water treatment. The two most commonly used coagulants are aluminum and ferric iron. The aluminum ion does not really exist as Al31, and the final product is more complex than AlOH3. When the alum is added to the water, it immediately dissociates, resulting in the release of an aluminum ion surrounded by 6 water molecules. Regardless of the actual species produced, the complex is a very large precipitate that removes many of the colloids by enmeshment as it falls through the water. This precipitate is referred to as a floc. Floc formation is one of the important properties of a coagulant for efficient colloid removal. And the next one is ferric iron. Iron can be purchased as either the sulfate salt or the chloride salt. The properties of iron with respect to forming large complexes, thus and pH curves are similar to those of alum. So those are the two commonly used coagulants. Next is we will be talking about the four basic types of coagulant acids. First, pH adjusters. Acids and alkalis are both used to adjust the pH of the water into the optimal range for coagulation. The acid most commonly used for lowering the pH is sulfuric acid. Either lime or soda ash are used to raise the pH. The second is activated silica. When activated silica is added to water, it produces a stable solution that has negative surface charge. The activated silica can unite with a positively charged aluminum or with iron flux, resulting in a larger, denser flux that settles faster and enhances emission. The addition of activated silica is especially useful for treating highly colored, low turbidity waters because it adds weight to the flux. However, activation of silica does require proper equipment and close operational control, and many plants are hesitant to use it. Third is clay. Clays can act much like activated silica in that they have a slight negative charge and can add weight to the flux. Clay are almost most useful for colored, low turbidity waters, but are rarely used. And the fourth is polymers. Polymers can have a negative charge, positive and negative charge, or no charge. Polymers are long-chain carbon compounds of high molecular weight that have many active sites. The active sites adhere to flux, joining them together and producing a larger and tougher flux that settles better. This process is called interparticle bridging. So for the next topic, it is all about water softening. Water softening is divided into four subtopics. First part is the chemical precipitation. Second is lime soda ash softening. Third is process treatment trains or softening. And lastly, other softening methods. First, what is water softening? Water softening is the removal of polyvalent cations from water that cause hardness. Hardness is primarily attributed to the divalent metallic ions, calcium and magnesium. The removal of ions that cause hardness can be accomplished by chemical precipitation, ion exchange, and membrane processes such as nanofiltration and reverse osmosis. Hard water does not lather well, so therefore, soap and detergent consumption increases. It produces a scum in the bathtub, shower stall, and on plumbing fixtures, and it produces scale in water heaters and boilers. So all about water hardness. Water hardness is primarily an aesthetic consideration. However, lime softening can effectively remove heavy metals, iron, manganese, natural organic matter, total organic carbon, and turbidity. Total hardness in water is defined as the sum of calcium and magnesium ions because these are the prevalent species present especially in groundwater. Total hardness is subdivided into carbonate and non-carbonate hardness. First, carbonate hardness. It refers to the portion of total hardness that is associated with the carbonate and bicarbonate anions. Sometimes it is called temporary hardness because it can be removed by heating the water. While non-carbonate hardness refers to the hardness caused by ions that are associated with non-alkalinity anions, and it also cannot be removed by heating the water, so it is called permanent hardness. So for calculating carbonate hardness, if the alkalinity in the water is less than the total hardness, the carbonate hardness is equal to the alkalinity, and the water must be treated with both lime and soda ash, where total alkalinity of the water is represented with the unit of milligrams per liter, while calculating non-carbonate hardness is equal to total hardness minus carbonate hardness, and it is expressed in milliequivalent per liter or milligrams per liter. When the alkalinity in the water is equal to or greater than the total hardness, the carbonate hardness is equal to the total hardness, and only lime addition is required for softening the water. So there is a table here that shows one method of classifying water with regard to hardness. So for the categories, there are soft, moderate hard, hard, and very hard. For its equivalent hardness, soft ranges to 0 to 50, while moderately hard ranges to 50 to 100, hard 100 to 150, and very hard more than 150. So for the first subtopic of water softening, it is chemical precipitation. What is chemical precipitation? Chemical precipitation of hardness causing ions has traditionally been accomplished by adding lime and soda ash to water. Soda ash may be omitted when the magnesium ion concentration is less than 40 mg per liter as CaCO3 and when the non-carbonate hardness is insignificant. The general form of this solution is presented as the solubility product is equal to molar concentration of cation species times the molar concentration of an ion species. So for the next topic, it's all about lime soda ash softening stoichiometric equations. The stoichiometric equation involved in the lime soda ash water softening processes are presented on the following slides. Although the reactions are presented sequentially, in reality, they proceed simultaneously. When quicklime CaO is added to water, it forms hydrated or slaked lime. This is an exothermic reaction. Carbon dioxide may be present in the source water and is denoted as CO2 aqueous. This represents the quantity of gaseous carbon dioxide that is dissolved in the water CO2 and is estimated using Henry's law. For groundwaters, carbon dioxide is typically present and at a much higher concentration than in most surface waters. It will be in equilibrium with carbonic acid as shown in the equation in the PowerPoint. If carbon dioxide or carbonic acid is present, it must be removed or neutralized before hardness-causing ions can be precipitated by adding chemicals. So for the next topic is the process trains for softening. Third topic is also divided into three subtopics, and these are single stage softening, two-stage excess lime soda ash treatment, and split treatment. First, single stage softening or selective calcium removal. Conventional softening treatment has focused on the removal of calcium carbonate hardness from water. Single-stage softening can be used on waters with a magnesium concentration less than 40 mg per liter.